All right, how's it going?
We go to aerospace today?
So any final questions on PA3?
Not really a reason.
Do I?
All right, PA3's all good?
Is the repository still supposed to be called HL?
The Git repository should be called HL uppercase, and the script should be HL lowercase.
Whoa.
Right? Yeah.
That's crazy.
Use those shift keys, man.
Nick, we talked about this. It's caps lock.
Yeah. Yeah. Totally.
I feel like I'm making fun of my typing. I noticed that you use spaces. And I'll be like,
What's that, what?
You use spaces when you're indenting.
Yeah.
Man.
Because tabs go in like 8 usually, so.
Yeah, but I don't know. Tabs are more consistent.
Depends how consistent your spaces are, I guess.
Yes.
Yeah. Whatever you're
We should
into is
watch
good.
Silicon Valley.
Ah, no, totally.
There's an entire skit in there.
Really?
Yeah. One of the main characters and his girlfriend just like break up over tabs versus spaces.
Nice. I could see that.
It's pretty fun.
Yeah. My brain is always at war internally over that, actually. It's been détente for like 30 years, but it's still like.
Yeah.
All right, so let's move on to PA4. Whoa, Grim Reaper's here. Uh-oh. All right, let's go on to PA4. So PA4 is back to C programming, okay? PA4 is a large C program, so you want to start it early. Hopefully from the description you'll know that you should believe this, but it's a long assignment. I've had students tell me this was the hardest program they ever wrote. But it's a good assignment, okay? It will give you exercise and lots of good stuff. So this gets submitted again through GitLab through a repository named index with an uppercase I. And make sure I have read access to it. So again, set that up day one, right, and keep pushing your stuff over there, and then you don't have to worry about backups. You don't have to worry if you oversleep on the morning it's due, and so on and so forth. So November 15th, 8 a.m., and the assignment goes bye-bye at 8:30. So, but that doesn't really change anything. All right, so let's look at the details of this. And I'll warn you, it's a 2-page assignment. So this is our longest so far. So high-level view, what are you doing? You're writing basically an indexer, something that takes a set of text, okay, just, you know, words, sentences, punctuation, things like that. And the goal is to break that input into phrases, so sentence fragments. So if you say 2 things with a comma in between, that's considered 2 phrases, okay? So pieces of sentences, it's going to break your input into these phrases, it's going to save them in memory, and it's going to record how many times it sees each phrase. So there's sample code available under /temp index-sample. So we can type whatever we want. This is some text. This comma is some text. So is this. So is this. All right, so if we were to just kind of logically think of this as phrases, we have the following phrases. This is some text. This is some text. So is this, hello, how are you, hello.
So phrases would end with punctuation?
So they end with punctuation. So I hit Control D to signal end of file. That's how we hit end of file when we're reading from the keyboard. And here's the output I get. So this appeared once, hello appeared twice. So is this appeared twice, how are you, and is some text appeared once, this is some text appeared once. And the output is sorted in increasing length of the phrases, so short phrases come first, And the number of times each phrase appeared is on the left, 5-digit integer with zeros filling in the spaces. So you're going to write a program to do this.
So is everything that you typed initially stored in one? Like,
No. I forgot to mention that at the last class. Yes, very important. You don't want to read the entire input in and save it in memory. You want to process this as you're reading the input. The reason being that one of your test files is War and Peace. So 3.2 million characters, 64,000 some lines of text, and 500,000 words. And your program should be able to chow on this, and it should process it pretty quickly. If you try to pull that into memory, you're going to have a lot of hard times. So /temp /index sample, I can say less than and give it the name of a file, like War and Peace. And that'll go through and break up War and Peace into phrases. And the shortest phrases are in the beginning, so I can pipe that into more to see the short phrases up top. So, oh, ah, no, who, but, and, yes.
Papa.
Okay.
Yeah, 1805.
If we add a way to sort by how much there is, like for example, well shows up 362 times,
Mhm.
but whom shows up only twice.
Yeah. You could add a switch for like changing the sort order if you want.
I feel like that would be interesting.
Yeah, that is interesting. We can also fake it here because the number of occurrences comes out in the left column and it's padded with zeros. If we just take this output and we pipe it through sort, we get this sorted by increasing number of times a phrase occurs. So the most popular phrase in War and Peace is yes, followed by well, followed by no. So it's probably a positive story. And Pierre said something 99 times. Prince Andrew said something 66 times. So you can start doing some interesting high-level analysis on text, if you like. Anybody here know Project Gutenberg? Gutenberg? Anybody here know who Gutenberg was? Yeah.
That's where they post like all the books online, right?
Yeah. So Gutenberg was the inventor of the printing press, which is, in some reckonings, the most significant invention in modern history because it really changed the world in a lot of ways. So Project Gutenberg is a site where reading material that's freely available, it's out of copyright, is posted and you can download it. And it's been around forever. So you can find sample text to chew on from there. So yeah, we could make a short version of War and Peace by just using each phrase once. All right, so that's sample text. Okay, so read lines from standard in, break them into phrases, store them in an array, record how many times each phrase occurs. When you get to the end of the input, print out the list of phrases along with the number of times it occurs, sorted in increasing length of the phrase. That's your 40,000 foot view. Details. First three details we can deal with once and never have to worry about again. First detail, convert all your letters to uppercase. So uppercase hello, lowercase hello, H with lowercase letters after that, all treated to uppercase HELLO. And this is easy to do if you know the function toUpper. So toUpper, you have to include ctype.h. You pass it a character, it says int, but it's really a character. Pass it a character, it gives you back a character, that's the uppercase version. All right.
Add to the ASCII.
It will in this case, yeah, but if you do this on an alien machine that doesn't use ASCII, it'll still do the right thing, whatever that is.
What?
Yeah, because this is part of the C library for this machine. If you're on a machine that's on an IBM that's using EBCDIC in the 60s, right, then toUpper would be different code, but it would do the right thing.
Whoa.
Yeah, so this is the right way to convert case. Okay, so that's your first detail. Second detail, any kind of white space you find, convert to a space. So if you find a new line, change it to a space. If you find a tab, pretend that it's a space. If you find a space, it's just a space. If you find 3 spaces, it's 3 spaces. But if you find a space followed by a new line, followed by a tab, that should turn out looking like 3 spaces. And the reason for that is that in your input text, you might have something like this: space is new line fun, period. Well, if you do this conversion, this will end up looking like this: space is space fun, period. And now when we're looking to see if something is a part of a phrase, we just have to say, is it a space? We don't have to say, or a tab, or a new line, or a form feed, or this or that, or the other thing. So that's another simplifying assumption, and that's really easy to deal with if you use the isSpace function. So isSpace is one of a slew of functions available from ctype.h. And if you go down to the documentation for it, checks for white space characters. This is a space, form feed, new line, carriage return, horizontal tab, and vertical tab. All of those will come back as saying, yes, this is a white space.
So once we find the phrase, we can run it through that and change
I would
it.
do this as soon as you're reading an input, though, because spaces will potentially affect what you consider to be a phrase.
For the Git in a repo, do you want to index in all caps?
Just an uppercase I. All right, third detail, ignore parentheses, single quote, double quote, and dashes. It's going to make noise, just go for it. There you go. All right, so ignore these 6 characters, these 5 characters, okay? When I say ignore, I mean don't ever process them. If you're reading characters and you come across a parenthesis, just throw it away and read the next character. So if your input is parentheses hello, you should treat it just like hello. Get rid of the parentheses. Okay, so we're going to do those 3 things up front as we're reading in characters. Convert letters to uppercase, convert any kind of space into just a single space, and ignore parentheses, quotes, and dashes. Just throw them out. Okay, with that understanding, we can define what a phrase is. And this can get you all tangled up if you try to get too intuitively close to it, but it's 3 sentences here that tell you how to find a phrase. A phrase begins with any non-space character other than these 6 magic characters. I'm just going to call these the magic characters. Period, comma, colon, semicolon, question mark, and exclamation mark. So a phrase begins with any non-space character other than a magic one. The phrase ends with one of these magic characters. When you get to a magic character, you've hit the end of the phrase. And that character is not part of the phrase. Everything in between is part of the phrase. So let's do some parsing. So the magic characters are dot, comma, colon, semicolon, exclamation mark, and question mark. All right, so okay, hello peoples, are you there? So that's our input text. Okay, first thing we're going to do, we're going to convert everything to uppercase. We're going to change spaces to spaces. I just have spaces here. And we're going to toss out any of the special characters we want to ignore. So this is going to end up looking like this. Hello peoples, are you there?
So if it comes with a cross and apostrophe, do you want us to throw it out but not count that at the end of the phrase?
An apostrophe gets thrown out, does not do anything to your phrases.
Okay.
So can't is going to be C-A-N-T.
Yeah.
It changes the meaning.
So let's add some more on here. This would be C-A-N-T. Help. Period. Alright, so the parentheses get tossed, the quote gets tossed. Yeah, I can change the meaning, but this is approximate. Alright, so a phrase begins with any non-space character other than a magic one. Okay, so if this is where we're reading, this is the letter H, that's not a space, it's not a magic character, that's the start of a phrase. And the phrase will continue as long as we find letters, characters, spaces, anything except magic. Okay, so spaces are included in phrases, so not magic, not magic, not magic. All of this stuff will be part of our phrase until we get to the comma. The comma is one of our magic characters. So all of this is going to be our phrase. Okay, and we've hit the end of the phrase, that was the comma. Now we go back and we say, okay, let's find the beginning of the next phrase. We want any non-space character other than a magic one. Well, there's a space, that doesn't work. Here's a non-space character that's not magic, that's the letter A. That's the beginning of the next phrase. We read all of that until we get to a magic character, which is a question mark. So here's the second phrase. Alright, beginning of the phrase is any non-space character other than a magic one. Well, that's magic, 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 that's a space. There's a non-space character that's not magic. So the C is the beginning of the next phrase. C-A-N-T space H-E-L-P, and the period is magic. So there's our third phrase, can't help. So for the most part, this is a reasonable approximation of breaking up a big sentence into small sentence pieces. It's not perfect. You can find things where it'll go funky. But if you wrap from one line to another because of a hyphen, right, the hyphen gets ignored. The new line will turn into a space, though. So it'll break a hyphenated word into two words. So it's not 100% perfect, but we're not worried about that. Right? What you want to do is follow those three descriptions of the beginning, middle, and end of a phrase. All right, so you got the idea of a phrase? All right, so the goal is to record how many times each phrase occurs. So if we've never seen hello peoples before, we want to record that somewhere and say this occurred once. Are you there? Record that. That occurred once. Can't help. That's new. So save that. That occurred once. If somewhere else we see the phrase, are you there? We should say, oh, we already saw that once. Okay, now we've seen it twice. So you're building up a dictionary of phrases that shows you the phrases you've seen and how many times you've seen each of them. Okay, so there's a sample input file smaller than War and Peace. Don't try War and Peace until you're sure your code is pretty much perfect. And then you can try that to sort of really give it the super duper acid test. But here's a small test file that you could work on. Or you can just, make up a file of input and try it like that. What you should do, though, is using this idea of what is a phrase, what's the beginning, what's an end, you should go through the sample input yourself on paper and convince yourself that this is the right output. Okay, for example, the word so appears twice, so that's pretty straightforward. Ha 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 appears once with a colon at the end, another time with a period at the end and an uppercase H, but those should be the same phrase, ha ha ha, that should appear twice, right? So you can use this on paper, you can work with other people on this if you like, on a whiteboard. Try to figure out how you're going to parse your input into these phrases. march through the input and do whatever you think your algorithm should be doing, convince yourself that it actually chops this up correctly. And here's the output you should end up with if you're playing along. But you can use anything for an input file you want. You can use source code and see how many times you use different statements in your C code. All right, ready for the pseudocode. So, an example of some pseudocode. Okay, so read, and I'll tell you what read means because I have a little asterisk next to it, but read from standard in until you find the beginning of a phrase. Okay? And then keep reading from standard in until you get to the end of that phrase, and as you're reading, store the characters that you read into a temporary array. And then when you're done, when you've hit the end of the phrase, your temporary array contains that phrase. Throw a null terminator on the end, right? And now, if it's a new phrase, save it in your dictionary with a count of 1. If it's a phrase you've already seen, just bump up the count. And then go back to step 1. And keep doing that until you hit the end of the input, end of file, EOF. Once you've hit EOF, sort the array by length and print out the phrases with their occurrence count.
So are we going to be doing something along the lines of a linked list or phrases?
You can just use an array. So just plain old two-dimensional array. But yeah, a linked list would be a nice approach. Alright, so you've done pieces of this in ODPs already, right? Let's say we're sitting right here and this is a non-space, non-magic character. It's an H. That's the first character of our phrase. So we can make, a temporary array called temp, for example, and we need some kind of output location that we initialize to 0. Well, here's an H. Let's store that at location 0, and let's bump up our output location. Get your next character. It's an E. It's not an end of phrase, so store that at output location 1, bump up our output location. Get the next character, it's an L, store that in position 2 and bump this up, and so on, right? When you're done with this, when you find the comma which says I'm done with the phrase, outlook will probably be the location where you want to store your null terminator. Okay, so this is similar to stuff we did last week. So do that, and now I have a character array, a string called temp, which has my phrase in it. So now I need to know if that's a new phrase or one I've seen before and do the right thing accordingly. So it's really 3 pieces. It's processing your input, breaking it into phrases and tallying them, and then doing a sort, and then doing your print to show the final result. Okay, so this read function, you can use getChar to read a single character from standard in. Okay, it's like fgets, but it just does one character at a time. My suggestion is make your own version of getChar, call it super duper getChar, and what super duper getChar does is it will convert letters to uppercase. So if you input a lowercase a, it'll give you back an uppercase a. If it gets any kind of white space, it'll just give you back a single space. And if it reads a parentheses, a quote, or a dash, it will call getChar again and get another character. And if that's a parentheses, a quote, or a dash, it'll call getChar again, and it'll keep doing that until it gets something that's not one of these characters we're supposed to ignore. So now it reads the number 2, okay, it returns 2. So you make your own super duper getChar function, and those first 3 details, don't have to think about them anymore. Because you know that super duper getChar always gives you an uppercase letter or a single space, and it's never going to give you one of these things that you should be ignoring. So that's maybe a good first function to write, super duper getChar. And convert white space, just do a call to is space. Convert to uppercase, just do a call to to upper. Ignoring these characters, that's a while loop. Okay, but you've done this before, right? When somebody puts in how many sticks they want to take, it's got to be a 1 or 2 or a 3, and you have a while loop. And you say if it's not a 1 or a 2 or a 3, get another input. Well, same thing. Get a character, and while it's one of these things you should ignore, get another character.
And we want to handle function files being input and stuff like that.
You're just reading from standard in, but if somebody redirects, it's going to look the same to the code. Yeah. All right. So, simplifying assumptions. This will save you a ridiculous amount of effort. It's still a really hard assignment, but it's way harder if you don't do the following simplifications. So you should assume each phrase has no more than 200 characters in it. Now there are going to be longer phrases in your input. For example, on War and Peace, we have a sentence here which says, drawing nearer to the prince, blah, 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 think how unfairly sometimes T, right? That was 200 characters. Now, having a sentence, a phrase that's longer than 200 should not blow up your code. It should not segfault, but you only have to store the first 200 characters. And if there's another phrase that has the same first 200 characters and different stuff later, just treat it as the same phrase. So if a phrase gets really, really, really wordy and is more than 200 characters, just look at the first 200, okay? But don't take, the rest of it as a new phrase or something like that. Let the phrase be 500 characters long, but just use the first 200. Okay, that's the first simplification. Second simplification, you can assume a maximum of 1,000 unique phrases. Now there's more than 1,000 phrases in War and Peace. But if you've already seen 1,000 unique phrases, you don't have to save any of the new phrases. But you still have to keep processing the file. You still have to keep tallying the phrases you've already seen. But if you see a new phrase, that's a new one, it's the 1,001st phrase, just ignore it. All right, so each phrase is 200 or fewer characters, and there's a maximum of 1,000 phrases. This means that you can make your dictionary just a statically defined array of characters, 1,000 long, 201 wide. So we can do this character dictionary. (1,000 by 201). Character dictionary, 1,000 long, 201 wide. And any time that you want to pass your dictionary to a function, in that function, when you declare the argument, make it a character argument bracket 1,000 bracket 201. Okay, it will make life a lot easier. The alternative is to make it a character ** dictionary, which is really what this is, but that introduces all kinds of failure modes. And you can make it a character * dictionary bracket 201, and it gets really confusing. And then if you start looking at this on Stack Overflow, you're going to see a whole universe of possibilities. Simplest way, just make it dictionary 1,000 by 201. And what does this mean? It means, for example, dictionary bracket 0 is a string. It's a character array of length 201.
So if you did int dictionary 100201, it would only store 1,000 integers that are as long as 201.
Yeah, it will let you store 1,000 arrays of integers where each integer array had 201 entries.
So it's an array of arrays.
Yeah, so it's an array of arrays. So dictionary 0 is a string. It's an array of characters. Dictionary bracket 1 is a string of 201 characters, all the way down to dictionary bracket 999. So you've got 1,000 strings stored in your dictionary, and each of those strings is a phrase. It's 201 characters, which means we can have 200 characters of any choosing, any 200 characters we want, and the last entry, 201st character, is the null terminator. So if your phrase actually has 200 letters in it, we can store all 200 of those and then throw the null terminator at the end. So these are 201. So dictionary bracket 0 is the first phrase. Dictionary bracket 1 is the second phrase. Dictionary bracket 999 is the 1,000th phrase.
How would we reference specific positions in the 1,000 addresses?
So,
Just be bracket,
Is it-
bracket, like dictionary, 0.
you mean within a phrase?
Yes.
Yes, so if I say dictionary bracket 1, bracket 1, bracket 15,
Okay, thank you.
that's the 16th letter.
That was all I was confused about. It's just
Okay,
a series
cool.
of brackets.
Yeah.
Series of bracketed numbers.
And you may not need to do that, actually. But if you need to, that's how you do it. All right, so this is how we can store our phrases. We can store them in this one array called dictionary. It's a two-dimensional array. We also need to know how many times each phrase occurred. So my suggestion is make what's called a parallel array. Make another array, which is an integer array. So integer count bracket 1,000. And the idea here is count bracket 0 is the number of times that dictionary bracket 0 appeared in the input. And count bracket 1 is the number of times dictionary bracket 1 appeared. And count bracket 999 is the number of times dictionary entry 999 appeared in the input. So we have an array of phrases, and next to that we have an array of counts.
Is there any fancy way to output the amount of counts, or when you just print out, you want to use the arrows?
Yeah, it's just a fancy printf. All right, so these are called parallel arrays. The nth entry here is the nth phrase. The nth entry in count is the number of times that phrase appeared. If you like structures, you can use a structure instead. You can make a new type of variable called dictionary entry that contains a string of 201 characters and an integer count. And you can make your dictionary an array of 1,000 dictionary entries. Okay, that's only if you want to try dabbling with structures or you like structures already. Not required to do that. Parallel arrays work perfectly fine, and they're great for this assignment. And we'll get plenty of chance in winter to play with structures. But if you want to make things more challenging than they already are, feel free to use a structure.
Did you use multiple files and separate out your functions, or you just did it in one big file?
Well, so that's an option. So I did both, and we'll talk about that next. So you can use functions from standard I/O, string, ctype, and standard lib. Don't use any built-in sorting functions. Don't use any built-in hash functions if you know what hash functions are. Write all the code yourself. Okay. Later on, we'll see how to do this in a different language called awk, and it's about 6 lines of code, because awk has built-in associative arrays. We can do that in C, but don't. Okay. Do it the long way. All right. Let me mention final notes, and then we'll talk about suggestions. So final notes, make sure you submit via GitLab. Make sure the repository is named index, uppercase, I only. Your submission must include a makefile, so we're going to talk about makefiles next week. Makefiles are a way to have a project that contains a number of pieces to it. It's a way to recompile your code really easily. And if you change one file, it knows what has to be recompiled. And anytime you want to make your project, you just say make, M-A-K-E, enter, and it makes your project for you. So we'll talk about makefiles, and you'll need to include a makefile with your submission. You need to document everything, and you really want to try to document things as you're working. Okay, we're going to be usually doing this by making your main program a bunch of calls to other functions, and those functions will be calls to other functions. There's going to be a lot of structure here. And you need a way to keep track of that, right? You can do 60 sticky notes all around your desk and your monitor, right? But put some comments in your code, right? Find a way to comment your code that's useful to you. That takes the place of those sticky notes, or at least works with them, so that when you want to know, okay, how do I call this function again, you have something in there that you know how to read and it makes sense to you. Okay, so play with commenting. Make sure you can handle long phrases and input that has more than 1,000 phrases without blowing up. That's the War and Peace final test. Sample executable is there under /temp, and War and Peace is a sample test file. You're welcome to try running each other's code. You're welcome to take input and ask people what they think it should turn into in the output, and so on like that. Just don't share code.
So the running thing, are our home directories set up so you can just run from them, but you can't read the code?
Say again?
So like the sample executable.
Mm-hmm.
If you wanted someone else to run your code, could you send them the executable, just copy into their home directory, or would you have to?
You could change the permission on it so that it's accessible by other students or by the world, and then just tell them to go /home /my name / whatever, right? Just don't do it to the source. Or you can copy to temp, but you know, temp is shared by everybody, so if you just call it PA4, probably somebody else already has a PA4 there. All right, so suggestions. Really try to think about breaking things down into modules, into pieces. Okay, and I know you've already been doing this on your other assignments, so you're ahead of the curve here. But this is a really good opportunity to modularize, to break large functions into smaller functions. And this is also something you can work on together. You can go in front of a whiteboard and you can try to spec this out from an algorithmic point of view, right? That's a great thing to brainstorm on, because there are a lot of ways to do this. Let me show you an example of a main program. So what does our main program need to do? Yeah?
The regular include files, the prototypes for the called functions, and the main function.
Okay, cool. So we've got includes, we've got function prototypes, and then we've got the main function. Okay, so and we don't have any command line arguments here, so it's just, you know, void or int main paren. So the actual code itself might be something like this. Read a phrase. Record that phrase. And then go back up to the top. And if you hit the end of the file, sort the dictionary and print the dictionary. And that's really it. That's all your main program has to do. Make a loop that reads a phrase and records a phrase until you hit end of file, and then sort your dictionary and print your dictionary. It's 4 steps. And your main program really might be only like 4 or 5 lines of code. Because I might say, well, not EOF, read a phrase, record phrase, right? These are function calls. And then outside my loop, I might say sort dictionary and print dictionary. You have a few more lines of code. And you got your includes and things like that. But your main program should be really small. It should probably fit easily on one screen when you're editing it. Now you can write this whole thing as just one main program, and it's going to be a few hundred lines long. It's going to be a real pain to work with and debug. But this is nice because it really, you look at your main program, you can tell exactly what it's doing. You put in a few good comments next to these, and it's really clear. Oh, here's my loop that's reading and recording my phrases, and when it's done, then I just sort it out and I print it. That's pretty simple. All right, sorting we're going to talk about next week. We'll go over a bubble sort. You've done bubble sorts before, I believe. It's sort of the easiest go-to sort, and we'll go through the algorithm for that. But that's just, just call this thing, pass it an array of strings, and it gives you back the sorted array of strings. Well, there's work you have to do in that, but you can write this function without doing anything else on PA4. You can just write a bubble sort function and pass it an array of strings. Well, how do you make an array of strings? You could declare it with curly brackets, right? Or you could just call fgets 5 times and save each thing the person types into the next element in the array, and then call your sort and print it out. There's lots of ways you can do that. Nothing to do with PA4. Just write your sort routine, okay? Print routine, well, that's really just a for loop, right? All you got to do once you print, if you know how many things you have in your dictionary, and you have the count, print out the count, a space, an angle bracket, %s, angle bracket, and the phrase. The leading zeros here, this is just %05D. So this says, make my number have 5 locations in the output, pad the beginning with zeros. So 1 comes out as 0, 0, 0, 0, 1. And D says an integer. Right? So this is really just one printf statement inside a for loop. So that's your whole print.
Do we need 5? Because if we're only going to 1,000, we only need 4, right?
Your phrase could occur 1,000,000 times.
Oh, that's true.
That's just 1,000 unique phrases. But yeah, hopefully it's not more than 100,000. All right, so sort and print, we can develop those. We can develop sort on our own. Print is really just a while loop or a for loop. That's not too bad. So the real trick is the phrasing. Okay, and these are separate tasks. Read a phrase is all of this other stuff. So how do we read a phrase? First you have to find the beginning of a phrase. Well, we can make a function to do this. We can have a function called is this the beginning of a phrase, and we pass it a character and it gives us a 1 if it is and a 0 if it's not. And how does it know if it's the beginning of a phrase? See if this character is not a space and not one of these magic things. If so, then it's the beginning of a phrase, otherwise it's not.
And you can do that in the get car too.
And you can do that in the get car, yeah. Super duper get car. Right? How do we know if something is the end of a phrase? Just see if it's one of those 6 characters. Well, put that in a function, right? You don't want to look at that code. It's going to be an if statement with 6 pieces to it, and maybe it's ands, and maybe it's ors, and maybe you get it wrong and you have to change it. Now you have to change it 15 different places because you wrote it 15 different places. Just make a function. Is this an end of phrase character? It returns 1 if it is, 0 if it's not, right? And now you don't have to look at all those punctuation marks. You just say, is it an end of phrase character? Is it a start of phrase character? And now our loop for reading a phrase is the following. Call super duper get car, get a character. While it's not the beginning of a phrase, get another character. While it's not the beginning of a phrase, get another character. Well, when you come out of that while loop, it's a phrase beginning. So now you store it in the output array, increment the output location, and make another loop while it's not the end of a phrase. If it's not the end of a phrase, store it in the output character, read another character. When you come out of that loop, you've hit the end of a phrase. Your output array that you've been building has the phrase so far. Pop on an null terminator, and you're done. You've read a phrase. Return that, and that's the whole read a phrase. All right, last piece is to record a phrase. Well, we have a dictionary with up to 1,000 entries, 201 each. You need to have some kind of dictionary length. Because arrays don't have a natural length in C. We have to keep track of their length separately. So dictionary length tells me how many phrases I've got stored in my dictionary. Well, this is a for loop. For I equals 0, I less than dictionary length I plus plus. If dictionary bracket I is the same as the phrase we just read, then I found my phrase. In that case, I want to bump up count bracket I. That's the number of times the phrase occurs. So just count bracket I plus plus, return. If I get through that whole loop and I've gotten to the dictionary length and I haven't found my phrase, I have a new phrase. So copy that into dictionary bracket, dictionary length, increment that, set the count to 1. Now you need to do details in here. You need to make sure that you don't have more than 1,000 phrases. You need to deal with end of file, because when you're reading from a standard in with your super duper get car and you're waiting for the end of a phrase, right, you might hit the end of the file instead, and you got to have a way to deal with that. So there's details in here, but again, this argues for trying to do things as modularly as possible. So those details get written into the description of what does super duper get car when it hits end of file. Well, that's up to you. You can make it anything you want.
What would it return?
So if you're building super duper get car on top of get car will return a -1 or EOF when it hits the end of the file.
So EOF would be like a string?
EOF is a symbol. You can just say EOF without quotation marks and it's set equal to -1. But use EOF. The last piece you probably want, there's a function called string compare. String compare takes two strings, S1 and S2, so you can look at the man page on it. And string compare returns something either negative, 0, or positive, depending on whether S1 is less than, equal to, or greater than S2. So if you want to know if S1 and S2 are the same, here's the only way to do it. If string compare S1, S2 equals 0, then you know they're equal. If they're not equal, you can't predict what it's going to return. It might be 1, it might be -15, it might be 103.
And does it only check length? Or
It checks to see if they're exactly the same characters and the same length.
Yeah.
And if you do this, that's not going to work for you. So if you want to actually compare character for character and see if two strings are the same, use string compare. Okay, you know about string length. The other one you might need is string copy. And there's manual pages on this. This copies one string into another. That's how you can load things into your dictionary. Okay, so that's a really fast run through on PA4, but that's all the pieces. So we'll talk about sorting next week. We'll talk about make files. We'll work more with some strings and some ODPs next week. Do some more string processing. And then later on in the week, we'll start going back to some more bash stuff. And we'll start playing with regular expressions and sed and awk. And
could we use regular expressions for this?
I'm going to say no.
Because that'll make it so much easier.
Exactly. All right, cool. Last reminder, no class tomorrow, so I will see you on Monday.